We will have one example of a memoryless system. In this example, we consider an y equal x of x to the power of 2. This is a very simple system, and this is a memoryless system because the output at time t, it depends only at x at the same time instant. So in this case, we can write a distribution of y. This is one random variable, this is one random variable, and the distribution can be easily written like that. This is what we have learned in your very early chapters. So remember that the distribution of x depends on time t. That's it. So the distribution of y can be given. So the second order PDF, if you take two samples at time t1 and t2, let's say this is time, then you can say, oh, I have the same two random variables. In this case, the Jacobian you will need to calculate, because the derivative of y1 with respect to x1 is equal to 2x1. The derivative of y1 with respect to other one is 0, and then you will have 0 and then 2x2, and the determinant of this is going to be 4 times x1 x2, and x1 and x2, they are plus minus the square root of y1 or this one, and in any case these will become 4 times the square root of y1 y2 when y1 and y2 are both positive. In this case, you can write the joint distribution of the outputs, the two samples of the output. Now, for instance, if you want to calculate y of time t1 and t2, then you need to calculate integral of this distribution times y1, y2. So if a random process x of t is normal with zero mean and a correlation function over x, therefore it is wide sense stationary, and it is also a strictly sense stationary. For such a random process, we can calculate this distribution, because this guy is going to become the Gaussian distribution, and then you plug it in there, and then we can calculate. So remember that a normal random process, which is wide sense stationary, is always a strictly sense stationary. Now, in this example, suppose that you have a square law detector. This function is called a square law detector, and it is widely used in radio communication, analog or digital radio communication. This is an analog circuit. In this example, if we calculate mean of y of t, you get this one, and obviously this is equal to Rx of 0. So the PDF of one sample of y we have calculated in the previous slide is equal to this guy, and if it is stationary, then this guy is constant. So the distribution is a gamma distribution with parameter of alpha equal to 1/2. So the autocorrelation of y time t, that means that this is equal to mean of y of t plus 2 and then times y of t. Obviously this guy is equal to this guy, and this guy is equal to this one. Remember that these guys, these two guys are normal. So I have product of 4 jointly normally distributed random variables. So remember that this is going to be equal to 2 by 2 samples. So I could say that this is equal to mean of the first of the 4 random, because you remember that if we say mean of x1, x2, x3, x4 as 4 jointly normal random variables, is always equal to mean of x1, x2 times mean of x3, x4 plus mean of x1, x3 mean of x2, x4, and then plus mean of x1, x4, mean of x3, x4. Now, so here, these guys, two of the random variable, these guys, another two random variables. So if we want to calculate this one, I will have mean of these two guys together and these two guys together. So I get rxx of 0 to the power of 2. And then I will have one of these with one of these and one of these with the next one. So I'll get plus twice rxx of 2 to the power of 2. So this simplifies to this relationship. So we can fully characterize different moments of the correlation of the output or even cross correlation between input and output. So the distribution of the input is Gaussian for this case. Then you have a square law detector. So this is the input to this system. And the output will have a gamma distribution with parameter of alpha equal to 1/2, which is this one. And if you give a random process like that to this system, the square of this one is going to be this signal, and then you can see that the autocorrelation function becomes something like that. So the autocorrelation function of the output is related is a constant plus autocorrelation of the input to the power of 2, of course a factor of 2 plus.